Hello everyone. In this video we are going to talk about numerical solutions of ODEs. This is continuing my previous video where I talked about implicit and explicit solvers. Here we're going to talk about errors. So we're going to talk about truncation errors, both local and global, and then the absolute error and relative error tolerance terms that you might see in ODE set command in MATLAB. So what do we have? Let's first talk about the truncation errors. Let's say, for instance, you want to solve this ODE y prime equals y minus 2t, where y of 0 equals 3, so it's an initial value problem, and we know the exact solution for it is y equals 2 plus 2t plus exponential t. So here, if we use three different solvers, the Euler method, the improved Euler method, or you might call one-step and two-step Euler method, and the Runge-Kutta methods, here we can see the error, and we can calculate error in this case because we have exact solution. So error here is the difference between exact solution and the approximate solution that comes from any of these methods, okay? And we look at the amount of error that we have in 5 steps, 50 steps, and 500 steps, okay? So the number of steps that we choose is 5, 50, and 500. And here we look at, let's say, y at a specific time point, right? So let's say, for instance, we start at y of 0, and then let's say if we want to find y of 1, which the exact solution is clearly, as you can see, 4 plus the Euler number, right? And then we might, as I said, get an approximation from this, and then we go from 0 to 1, one time with 5 steps, so 0.2.4 all the way, one time with 50 steps, one time with 500. And you know, if we make the number of steps bigger or the step size is smaller, we get better accuracy. So of course, we need to use more evaluations of the right-hand side function, but comes with that extra computation, better accuracy. So at 5 steps, we have something times 10 to the negative 1, 50 steps. When we go up by an order of magnitude, the error drops by an order of magnitude. And when we go again up by another order of magnitude in the number of steps, again, the error drops by another order of magnitude. So you see that the error is proportional to what? To the number of steps in a linear manner for Euler. Now for improved Euler, look. When I go from 10 steps to 100, the error goes from 10 to the negative 2 to 10 to the negative 4. Then I go another step, it goes 10 to the negative 6. So you see error here is proportional to the number of steps, if we call them n, right? It's proportional to what? To the number of steps squared. Of course, 1 divided by that, huh? Yeah, so if you make the steps 10 times bigger, the error drops by 100. Here, you see that the error is proportional to directly to the number of steps, right? Here, 1 over n. And if you look at Runge-Kutta here, when I jump by a factor of 10 each time in the number of steps, the error drops by 10 to the negative 4. So here, this is proportional to 1 n to the 4, okay? That's why we say Runge-Kutta is basically the most accurate among these three, because the smallest change in the number of steps will be resulting in a lot better accuracy, a lot smaller error, okay? And this is exactly what I told you. Now, using this, we can define what? The local truncation error. How? Let's say if we start at time t equal tn, and at this point, let's say we know the exact solution. Now this tn could be t0, for instance, like here. I know the exact value at t0, and I want to go to t1. I just want to move one step forward, assuming that in the previous step I knew the exact solution, and assuming that there is no round of error, I want to know how much error will be created due to applying one step of a solver. That is what we call a truncation error. For instance, if we go back and look at the simple or one-step Euler method, what do we have? So let's say the equation we want to solve is y prime equals f of t and y, first order ODE, and let's say the exact solution, we call it phi of t. If phi of t is the exact solution, then phi prime of t is clearly f of t and phi, right? So if you plug it into the equation, it will be held, right? And again, let's say at t equal tn, we know the exact solution, so the value we pick, yn, is phi at tn, okay? Yes? And of course, because phi is the exact solution, if I plug it into my equation, then phi prime at tn equals what? F at tn and phi n. Okay, so from 3 and 4, we can get from, 1 and 3, we can get what? We can get basically 4, right? And from the fact that it's the exact solution, yn equals phi of tau n. Good. Now, as I said, we're going to take one single step, and let's say the step size is h. And we're going to use the simple Euler method. If we do, what is the Euler method says? It says the new y equals the old y plus the step size times the right-hand side function evaluated at the current t and the current y. Yes? Now, if I combine 3, 4, and 5, what do I get? So yn was phi of tau n, so I just plug it in directly from equation 3. Then f at tn and yn, again, yn is phi at tau n, so I just plug it in. And then remember that f at tn and phi n equals what? Equals to phi prime at tau n, right? So here, I replace that from equation 4. So now yn equals what? Phi of tn, phi at tn plus h times phi prime at tn. And since my step size equals h, so my next time point, t at n plus 1, equals previous tn plus h. So if that's the case, the exact solution at the next time point, phi at tau n plus 1, is equal to phi at tn plus h. And then here, I'm going to what? I'm going to expand this phi of tn plus h using a Taylor expansion. So it's going to be phi at tn plus phi prime at tn times h plus 1/2 phi double prime at tn h squared plus the cubic term all the way, right? So this is what? This is the Taylor series. Okay, now what is the error at the time t of n plus 1? It is the difference between exact solution and, of course, what? The approximated solution. Yes? Okay, this is the error at n plus 1. Now, what do we do? For phi of t plus n, we directly bring it from this top equation. And for y of n plus 1, we bring it from this other equation. So if I call this, for instance, 6, and I call this 7, from basically 6 and 7, correct? From 6 and 7, I can get what? I can get that error equals. Here is that Taylor series for phi of t plus n, and this is what? This is the right-hand side of equation 6. What happens here is this phi n and this phi prime n times h will be simplified from both sides, so all you will be left with are cubic term, square term, and the higher order term. And if you want, you can write it as some k times h squared plus a term of orders h cubed and higher. Okay. Now this k term here is clearly 1/2 of phi double prime at tn, and I don't know it because I don't know phi. Remember, phi, the exact solution, is unknown. If I knew it, if I had exact solution, I would never use numerical solvers. So I don't know it, therefore I cannot find this k, but this k, if we assume it's some constant at this point, you clearly see that the error is proportional to h cubed and, of course, higher order terms. Good? Yeah? So this is what this is called the local truncation error. How much is it? You see it's proportional to h squared, right? Okay, yeah, that's for simple Euler method. Now here, what did we do? We started at time tn and we went to time tn plus 1. All we did was one single step. On the other hand, if we start at time t0 and assume that we know the exact solution only at time t0 and with no round of error, we want to apply n steps now and then find the error due to n steps of using the solver. That error is called global truncation error. Okay, so here the error was the difference between phi at tn plus 1 and y at n plus 1. This time the error is going to be what? The phi at tn minus y at tn, but starting at t of 0. So let's say at y0 the value is y naught and y prime still f of t plus y. At the nth step, the step equals tn equals time equals t0 plus n times h. And epsilon n here is phi of tn minus y, and this is the term, as I said, that we are going to calculate, and we call it what? The global truncation error. Now let's see how we calculate a formula for global truncation, because the local one was quite a bit easy. Okay, we did it pretty easy, but the global one, the extraction of that, the derivation of that is a little bit more involved, so bear up with me. So what we do here is we also try to derive a relation. If we call the global error at tn epsilon n, we also try to find a formula or a relation for epsilon at n plus 1, which is the difference between phi at n plus 1 and y n plus 1. Now remember that y at n plus 1 equals yn plus f h at, right? H at f of tn and yn, right? That is the Euler update equation. So remember, this is what? This is the Euler update equation. So here, I just plug that, and so both terms will get a negative. Now what? Now here we do a little bit algebra. What is the algebra that we do here? Let's take a look. So the algebra that we use is this term phi of t plus n is still here, as you can see it, okay? The term negative yn is still here, and the term negative h times f is still what? Is still here. You can see it here. So what have we added? Let's take a look. The terms we have added and subtracted to keep it the same as before is this positive phi of tau n and this negative phi of tau n. We added that, yes. Then what? Then we also added this term here, which is h times f at tn and phi at tn, and then negative of h at ftn and phi of tn, right? So we added and subtracted the black and the green terms, and the rest of them, the blue terms, are coming from the top. Now each portion of this formula 3 for epsilon of n plus 1, each portion of it has a meaning. What is this one? Well, clearly this is the error in the previous step. That is exactly the definition of what? Epsilon n. So this is epsilon n. So epsilon n plus 1 equals epsilon n plus. Let's take a look. What is what? What is the third term here? So let's look at this third term, this last bracket. What do we do? Let's assume that the magnitude of the second derivative of the exact solution is less than a for any t. Okay, so here we make an assumption on the second derivative. So the curvature is less than something, magnitude of it. And so Here, phi at Tn plus 1 equals what? Equals phi at Tn plus phi prime at Tn times h plus basically these higher order terms. In general, here is just an approximation, but there are these higher order terms. Yes? Now, knowing that the magnitude of these terms drop as they go forward, the magnitude of this guy here is less than that. So I can say that the magnitude of both of these together is less than what? Less than 1/2 of phi double prime h squared plus another 1/2 phi double prime h squared, right? So this is less than, if we add them, just going to be phi double prime times h squared, and know that your magnitude of phi double prime is less than a, so this is going to be less than a times h squared. And that is exactly what you can see here. So I can say that this third term in equation number 2 is what? This third term in equation number 2 is less than or equal a times h squared. The first term is epsilon n. Now let's focus on the second term here, this guy. Let's focus on that. So if we use the mean value theorem, f at t1 and phi of t1 minus t1 and y1, the absolute value of that is equal to absolute value of the derivative of the f at some point inside the range. And then what? Between, and by inside the range mean between yn and phi of tn times the difference between phi of tn and yn. Remember, the mean value theorem says that if f is a continuous function, right? So this is f and this is x. And if I have 2 points, x1 and x2, and this is f of x1 and f of x2, just telling you in case you forgot that, then if this is my function, I can find a point somewhere between x1 and x2 such that the slope of the line connecting the 2 points is equal to what? Equal to the derivative of the function at that point. Okay, there is a point for which the derivative is parallel to the line connecting the two endpoints, from where the f prime at that x star is equal to f2 minus f1 divided by x2 minus x1. If you cross multiply it and take absolute value, you exactly see this formula here. Okay, and this right hand side here is epsilon n, so the term is going to be equal to the derivative of the function. And here we make another derivative about f with respect to y, and we assume that the magnitude of f with respect to y at all points is less than or equal b. So that's our second assumption. Remember, our first assumption was this about the second derivative of the exact solution. Here we are talking about the derivative of the right hand side function with respect to the solution, first derivative less than b. Then we can say that the second term here is what? Except for the h of it, it's less than or equal b times epsilon n. If you put all of that together, then what's going to happen? Then the right hand side of this equation 2 is going to be epsilon n, and then this is equal to, the second term is less than or equal to h times basically b times epsilon n, right? And then again, less than or equal a times h squared. Okay, so that is going to be like this, right? And if I take absolute value and then I combine these two terms together, then I'll get this one. Okay, yeah? So now let's expand this formula for a bunch of different n's. see what we get. So first time we write it for n equals 0. If we write it for n equals 0, we'll see absolute of epsilon 1 is less than or equal 1 plus ph, absolute of epsilon 0 plus ah squared. Now at time 0, since we start with the exact solution, epsilon 0 equals 0. So it's just equal to ah squared, then absolute epsilon 2 less than or equal 1 plus ph epsilon 1 plus ah squared. And then for epsilon 1, we replace it with ah squared here. Okay, so you're going to get this, right? Then we go to epsilon 3. And again, for epsilon 2, we're going to replace it right here. So epsilon 3 is less than this guy here. And if we keep going and basically keep using these formulas that we all started from epsilon 0, 0, you'll see that the magnitude of epsilon n is what? Is less than or equal this guy here, which if you look at it, this is what? This is a geometric progression where this term here, ah squared, is basically like your initial term, and then the term that is raised to some power and the power is changed is this guy here, 1 plus bh. Here is like 1 plus bh to the power 0. Okay, so if we call that 1 plus bh your r, okay, then this can be written as summation of m goes from 0 to n minus 1 of a times r to the j. Okay, now here there is clearly a typo here as far as I can say, because if this is m, then this should be m2. So this is m, not j. And a r to the m, and of course you all know the value of summation of a geometric progression. If the magnitude of the r term, which is this, less than or equal 1, less than 1. If that's the case, then your epsilon n magnitude is going to be r to the n minus 1. This is r to the n minus 1 over r minus 1 times a. And if you simplify this, you get what? You get this term here, a over b times 1 plus bh to the n minus 1, the whole thing times h. And here I'll do one extra thing, and I call this bh term x. Okay, and clearly then this is going to be 1 plus x to the n, right? Now here h is the step side, which is positive, and b here is the value that is bigger than the first derivative at each point, so b is also positive, so I can say x is positive. Therefore 1 plus x here is less than 1 plus x plus all these other positive terms. Now we know if you add all these other positive terms, which have a form n x to the n over n factorial, right? If I add all of them, then this right hand side is simply exponential of x. So I can say 1 to the x is less than exponential of x for a positive x, and now it's time to raise both sides to the power n. And so that is this guy, which is less than or equal a over b times basically exponential of x minus 1 times h, right? And that is exactly what you can see here. Of course, this is to the power n, so here you have to also multiply it by power n, because we have this. And that is, if you write it, this is this one here. Okay? Because n times x is what? N times x is n times b times h. So it's like this. And n times h is the difference between tn and t0. So I can write it as e to the tn minus t0 times b, and that is this guy here. And finally, I found a formula which is an upper bound for what? An upper bound for the absolute truncation error. It depends on this a, It depends on this b. And of course, the important part is this. Forget about all of those. The important part is this. Pay attention to this part. That as n grows, this error grows exponentially. Okay, so you see here, it is Tn minus T0. So if n is 1, it is e to the what? It is e times b, and then T1 minus T0 is simply h, right? Minus 1 times h times b over a. But if n is 2, we have b over a e to the 2bh minus 1 times h. You see, and this is completely obvious. It's accumulation of error. As you move further into the time, your errors are going to accumulate. This local one that you had only for one step is now going to go to the next, to the next, to the next, and the accumulated error is going to be a form what? A form exponential. Okay, so that is the important thing that I wanted to clean up for you. That as you move on with further time steps and you move on in the time domain or in the independent variable, whatever it is, expect that the error of your numerical solution grows exponentially. Okay, and that is very important. Okay, so now that we know there is error and this error is going to go bigger and bigger, what can we provide to an ODE solver like ODE45 or anything like that we use in MATLAB, so we keep our errors below some threshold? We don't want our error to grow big with this exponential form, and after so much time our error is so much that our numerical solution is literally useless. Okay, so do we have any upper bounds? Do we have any controls over our error? If you look at the command odeset in MATLAB, there are two important tolerances for error. One is called the relative tolerance, the other one is called the absolute tolerance. Okay, and we want to know what these two are. So the absolute error tolerance in MATLAB, for which the default is 10 to the negative 6, it is a threshold below which the value of the solution becomes unimportant. What does that mean? Means if the magnitude of the solution, absolute value y, is less than this number, whatever it is, you can change it, then the solver does not need to obtain any correct digit in y. So if you look at this graph, which I got from MathWork website, that kind of can tell you that if this is my state or this is my solution versus time, in regions where the solution, the magnitude of the solution, falls less than this absolute tolerance, right? The magnitude of the response is very small. In such regions, basically, as I said, the solution becomes unimportant to you. Okay, so we don't really care much about the error of it because the solution itself is very small. It's less than 10 to the negative 6. So the truncation error is not that critical at this level. Now, on the other hand, if the magnitude of the solution is not super small, then the relative error tolerance is important. The default of it is in MATLAB is 10 to the negative 3, and we call it relative error tolerance because it is measured with respect to the magnitude of the solution. Okay, so in order for this to be implemented, it has to be multiplied by magnitude of the solution before your error can be compared to it, right? For the absolute tolerance error, we did not care about the magnitude of the solution. It was small anyways. Okay, and we just directly looked at what? We directly looked at this allowable tolerance, right? When the magnitude of x is basically very small, or you might call it y. This is your independent variable. Okay, but in the relative case, this is where you look at the amount of relative error or tolerance and multiplied by the magnitude. That will give you the allowable error. Your error should fall within this region, and you see that as the magnitude drops, because this magnitude x drops, these two envelopes also get smaller and smaller and get what? Closer to your actual solution. So that means what? If you have an approximate solution from Euler, Rankota, or whatever, it has to stay within these two dash envelopes. So if I have a solution like this, it is acceptable. Why? Because in the regions where magnitude of the solution is not small, it stays within the relative tolerance, right? These two. And in the region where the magnitude is small, it stays within the absolute tolerance zone. So it is fine. But if I have a solution like this green one, clearly this green one is within the absolute tolerance zone, but not what? Within the relative tolerance zone. Or if on the other hand, I have a solution like, let's say, this blue one, where in the relative zone is good, but when it comes to small ones, it goes kind of like this, then it passes what? The absolute. It doesn't pass the absolute tolerance zone, okay? So this relative and absolute, they give us some envelopes within which we can stay. And how do we combine them? We say that the error should be less than or equal maximum of relative tolerance times absolute value of the solution and what? The absolute one. And again, here you see y, here you see x, so that might be a little bit confusing. Therefore, I change this also to what? To y, so these notations are not confusing to you. Okay, yeah? So your local error E should be less than or equal this formula here. If it is, I'm good. If it is not, then what should I do? I have to change my step size. Okay? If my error is not less than this value, this upper bound, then I have to change the step size. I have to change this h. Okay, because you clearly see that when h is dropping or the number of steps is increasing, clearly your error is what? Getting smaller and smaller. Right? So the solution is to drop the size of the steps, the step, right? Make the h smaller. The question is how much smaller? So you can go, for instance, reduce it by a factor of 2 and see whether it works. If it works, fine. Otherwise, you drop it another factor of 2 and so on, which we'll see. We call it a refinement. And the next topic of the next lecture are the variable step size solvers, where they don't change this h to some smaller value forever if it fails in one step, and then just keep using that. In the regions where h has to be smaller, they make it smaller. In the regions where a bigger h would still satisfy this equation, they allow h to be bigger. Okay, and that is our next topic that we are going to see. It is called what? It is called basically variable step size, and we're going to see these amazing solvers, including OD45. In some regions, as I said, they use smaller step sizes, and in some regions they use what? Bigger step sizes, as opposed to using the same step size all over the place. Okay, so before I move into that, I needed to explain these error terms for you and how something like MATLAB calculates the upper bound of the error, right? Then I can go ahead and explain to you the variable step solvers, and finally the stiff equations. So hopefully the video was useful to you. I'll see you in the next lecture. Thank you.